to wrap up the string implementation. There's a couple of things I need to talk about before we do, though. So number one, when we implemented our string, we put some stuff in a header file, right? So all of our functions were declared in a header file, but we also defined our structure in the header file itself. So C has no notion of access modifiers like Java has private or protected or package private. Right? So there's no way to restrict visibility once you give it to somebody. So as soon as you define a structure that anybody can look at, and if you put it in a header file, that's going to be the case, right? Then anybody who's using the structure knows exactly what's in the structure. So everybody knows our string has a length, a capacity, and an array of char to hold the characters. As soon as you give programmers access to stuff, they're going to use it. So for example, someone can come along, include your header file into their program, and then they're going to do something like make a string. So they're going to make the string all caps hello, and then they know that they have access to the data or the data array belonging to your string. So they're likely going to go in and manipulate the data array directly, right? So rather than using our set method, or sorry, set function, they're going to, it's possible to go into the array directly and modify the array. And this is a perfectly acceptable and normal thing to do in C. There's no notion of visibility hiding in C. The best that you can do is try to hide this. Right? So in other words, don't tell people what's in your structure. And the way you do that is by declaring the structure but not defining it. Right? And so we're going to make what's called, you can make what's called an opaque type or an opaque struct. Right? They both mean the same thing in this case, right? So in the header file, instead of defining the structure, all you do is say that the structure exists. Right? So struct QString semicolon says that there is a structure called QString. Its definition is somewhere else. Right? Now in your source code file, you place the definition of the structure. Oops, sorry. Right? If you don't distribute your source code file, right? In other words, you only distribute the header file and the precompiled source code files, there is no easy way for people to know that your structure is defined like that. Right? With a little bit of effort, a competent programmer can figure out what's inside the structure. Right? So there are tools that will let you look at the compiled code, and you can figure out that the structure actually consists of these field members here. Right? So there's no real data hiding in C, but you can create an opaque type, which sort of gets you there. Right? So an example of an opaque type, which we'll see, I guess, next week, is this type called file, which we're going to use when we start to read and write files. Okay, so if you make your types, if we make this change, so in our header file, we only declare the type, we're going to have to add some functions to our string type, right? So we're going to have to provide people with a function to get the length of the string, because they can no longer go in and just look at the length. Right? And we're also going to have to provide people with a way to access this array because they may want to treat your QString like a C-style string, right? In which case they need the C-style string that corresponds to our QString. So we'd have to add some functions that give people access to our data members. Right? But that's not a difficult thing to do. All right, so many libraries that provide a data type, they often provide the data type as an opaque type. So in other words, if you grab someone's third-party library, typically in C what happens is you get a header file and you get precompiled source code files. Right? You don't get the original source itself. So you get what's called an object file or a library file that contains the compiled version of the code. So you can never see the actual definition of the structure that defines the type. There is an important advantage for doing this, and I guess most students at your stage, so in second year, for example, and you probably haven't worked with very large code bases yet, you probably won't appreciate this. But there is this thing called binary compatibility, which you can only achieve in C by using opaque types. So binary compatibility means that if someone changes, so for example, if we change the QString type, Imagine we provided the QString type and we shipped it to a bunch of customers, right, as pre-compiled object code. And we decide that we either find we find a bug, or we find a bug that we want to correct, right, or we add we change the way some of the functions are defined. If we don't provide binary compatibility, then when we ship our updated library, everybody has to recompile their code. Right? So in other words, if people can see the structure and we change the definition of the structure, people will have to recompile their code when they get the new version of our library. Right? If we hide the implementation of our structure from people, when we make changes, it's possible that people don't have to recompile. Instead, they only have to relink their program, which is much faster than recompiling their program, especially if their program is large. Right? Okay, so here. When we implemented all of our functions that returned QString objects or manipulated QString objects, right? They manipulated the objects by pointer. So QString new returns a pointer to a new QString structure. Right? It is possible for the QString type to return a structure itself, right? So instead, not return a pointer. Similarly, you can change all the functions so that they take in QString objects rather than pointers to QString objects. If you pick choice number 1, then the compiler needs to know, right, how big is the returned structure, right? Because it needs to allocate the correct amount of space for the returned object. Right? In the second form, where you return a pointer, right, the compiler does not need to know how big the QString object is. Right? It's returning a pointer to an object, and pointers in C all have the same size. Right? So the compiler knows it can allocate enough memory for a pointer, and it can store the return value in that piece of memory. Right? So if you choose this form, right? So in other words, if you choose to implement your data structure such that you return the structures directly, then any changes in the way that the structure is implemented means that people have to recompile their code. Right? If you return pointers to objects instead, then it's possible that people don't have to recompile their code. They may just have to relink to your updated version of the library, right? Which saves them a whole recompile, which saves them from recompiling their entire program. Right? Very large programs can take a very long time to compile. Right? Most students who've only seen small programs click a button somewhere or type GCC something and it compiles immediately. But it's not unusual to find builds that take hours or days to compile the program. All right, so opaque type, declare the structure, but don't tell people what's in it. Right? You define the structure in a source code file somewhere, right, which is hopefully hidden from other people. Okay, so that wraps up the QString notebook. And I guess we're ready to try another data structure. All right, so the next notebook is implementing a stack. If you're in 124 now, we're actually a little bit, this may be confusing for you because we haven't talked about how to implement a linked stack yet in 124. If you've taken 124 and you remember how these linked structures work, this should be a breeze for you. Right? So just quickly to remind you what a stack is, right? So a stack is a data structure that conceptually represents a stack of stuff. Right? So here we have a stack of files, stack of books, a stack of pancakes. Right? In a stack, everything happens at the top of the stack. Right? And so the only operations that you have manipulate the top of the stack. So adding to the stack adds another book on top of the stack. Removing the top book of the stack takes the top book off the stack. Right? And if you remember, the stack operations are called push and pop. Right? Those are the standard names for them. Although some people use the queue names. So some people will call these NQ and DQ. And vice versa for a queue. Some people will tell you it's push and pop for a queue as well. Right? Okay, so instead of using an array to implement the stack, we're going to use a linked sequence of nodes. Okay, so remember assuming you've taken 124, right, with me anyway, not in the summer. A node is just an object that stores a value, right, which we're going to call the element. right? And it stores a link to the next node in the sequence, right? And so here, this is a stack of this represents a stack of size 1 that's got 1 that has a value 1 on top of the stack, right? So there's one element in the stack. This link here points to the next element in the stack. There is no next element, so it's set to null. How would you implement this in Java? Right? So you could implement this thing here as a node class in Java, like that. Right? So you would have a, if it's a node that holds an int, right, you would have a field of type int that is the element, right? And then you would have a reference to the next node, right? If you guys have taken 124 already, hopefully at this point you appreciate the fact that the only reason this works in Java is because this is a reference to a node, right? It's not an actual node object here. Okay, so if you wanted to make a sequence of nodes, you just make a bunch of nodes and stick and join them together. Right? So in Java, make 3 nodes, N1, N2, and N3. Right? N1 is going to be my first node in the sequence. Right? So I can set its element. I want to make the sequence 1, 2, 3. So I can set the first element in the sequence to 1. Right? And then in N2, I'm going to set its element to 2. And in N3, I'm going to set its element to 3. And now I want to join the 3 nodes together. So I want N1 to link to N2, right? So in Java, you just write N1 next equals N2, right? So N1 next is a reference to node N2, right? And to join N2 to N3, you just write N2 next equals N3, right? So N2 next is a reference to node 3. And N3 is the end of the sequence, so we set it to null. Right? You can do the exact same thing in C, just using a plain old struct, right? Right, you can use a struct, and you can, for your next link, right, it's a pointer to a node, right? It's not a plain old struct node here, right? It has to be a pointer to a node, right? If you make it a plain old struct node, you don't actually get a linked sequence. Right? So it has to be a pointer to the next node in the sequence, right? And these lines here are going to be basically the analogous lines in C. Right? So to make N1, you can just make the structure, right? N2 and N3, right? You can set N1's element like that, right? Just the same as you would in Java, right? And to set the next link, right, you need a pointer to the next node. Right? So that would be the address of N2 in this case, right? And for N2, you want a pointer to the next node, so that's just the address of N3 in this case. Right, and of course, N3 ends the sequence, so you set its next link, its next pointer to null. Right? And this sequence would work fine as long as you only needed this sequence in one function. Right? So, for example, if it's the main function, that would be fine. If this was any single function, that would also be fine. Right? As soon as you try to do something like return this sequence, so you want to return, say, N1. To a calling function, right? This all falls apart, right? So why does it fall apart? Right? Because these all have automatic storage duration, right? So when you link N1 to N2, right, and if you return N1, right, N1's next pointer is invalid after the function returns, right? Because N2 no longer exists after the function returns. Right? And now your sequence is completely busted. Right? So what do you have to do instead? Right? You have to dynamically allocate these nodes. Right? So rather than make plain old struct node objects, you're going to dynamically allocate node objects, right? Using malloc or calloc or whatever you want. Right? So we're going to make a node, a pointer to a node in this case, right? And we're going to dynamically allocate memory for the node. Right. And of course, now when you go and set the elements and next links in your nodes, you're going to use the arrow notation, right? Because we're now working with pointers to nodes. Right. So M1, elam is 1, right? And N1, its next pointer points to N2, right? Not the address of N2 here, right? N2 is already a pointer, so I don't need to take its address. Right. And now, if you return N1 from this particular function, right? Whoever gets the returned pointer now gets a pointer to a sequence of length 3. Right? These things all have managed lifetime. right? So as long as you don't free the nodes, they exist. So returning N1 gives you the full sequence of nodes, which is exactly what you want. Okay, so how do you implement a stack using a linked sequence of nodes? Well, it's pretty easy, right? Where's our node? Our node is here, right? If you want a stack or a queue or a list made up of linked nodes, right? All you do is you make another structure called stack, list, or queue, right? And inside that structure, you have a pointer to the first node of the sequence, right? And then you might keep other information as well, right? Like how many nodes are in the sequence. I'm just going to scroll past all this because it's pretty straightforward, I think, if you've taken 124. Oh, I guess I have to jump pretty far ahead. So I'm going to jump forward and then I'll jump back. Where is my structure? Sorry, I'm looking for the structure definition. And I guess I didn't put it in. It's going to be in the source code file. So I'm just going to jump ahead. Okay, so in Java, if you wanted a linked stack class, right, you would nest your node class inside linked stack, right? You would have a reference to the top node in the sequence, right? And you probably would keep track of the number of nodes in the sequence. So in C, we're going to have a linked stack structure right there. Right? I'll explain the funny tag name in just a second. Right? So you're going to have a linked stack structure that keeps the number of nodes in the sequence, right, and a pointer to the top node of the sequence. All right, so that's going to be our stack type right there. So let me back up now, all the way back to the top of the notebook again, and explain what's going on. All right, so we're going to use an opaque type to define our stack type here. So when you have an opaque type, we're going to declare our structure. Right, so struct q stack or something like that. I think we're calling it ql stack here. And you're not going to define what's in the structure in the header file. Right? So in your source code file, you're going to define the actual structure itself. Right? Now, one of the one of the quote-unquote problems that you run into when you start to work with structures is that the struct word becomes part of the type. And that might annoy you. Right? So instead of writing struct ql stack everywhere, it might be nice if you could just write ql stack. So there is a way to shorten the name of the structure name, the full name of the structure to something else. Right? And so the way that you can shorten it in C is with something called a type def. Right? So in C, a type def lets you give an alternate name to an existing type. Right? So the way it works is it's the keyword type def followed by a space, followed by the name of the type that you want to shorten. Right? So for our string, we would write type def qstring, type def struct qstring, right? And then you give it its shortened name, right? So your alias is your new name for your type. So for example, we might just use qstring instead. Right? And so once you do that, instead of writing struct qstring everywhere, you can just write qstring. Right? Like so there. Right? So given our previous qstrings, given our previous structure that, right? If you write that type def, right, you don't have to write struct qstring everywhere. You can just write qstring instead. Right? If you want a pointer to a struct qstring, you just make a pointer to a qstring instead. Right? So that is arguably nicer to read than that. Right? Although there are many people who will argue that you shouldn't do this. Right? So in other words, there will be fairly prominent C programmers who say you should never use a type def just to remove the word struct from things. The fact that it's a structure actually tells the C programmer something, right? Whereas if you just get a type name, you don't really know what that means, right? Because you can alias anything with a type def, right? So for example, you could write type def int and then some funny name, right? And now you can use the type some funny name, and that's really just an int. Right? So there are people who argue that the type defs actually hide information from the programmer. Right? If you're using a structure, why don't you say you're using a structure? Right. Okay, so when you're implementing an opaque type, it's usually okay to use a type def to hide the fact that it's a structure, because it's an opaque type anyway. Right? You don't know, no one knows what's in the type. That's the point of making an opaque type. So the fact that it's, whether or not it's a structure or something else, it doesn't matter. Right? And so we're going to use a type def here for our stack. Okay. The weird thing in C is that you can write that. Right? So you can write type def struct qstring, where that name and the type def name are the same. Right? And it's strange. You wouldn't think you'd be able to do this, right? Because that name there is the same as the tag name belonging to the structure here. Right? But this works in C. The reason it works in C is because the tag name that belongs to the structure, right? So that Q string, if you remember way back now, a couple of weeks, when I first introduced structures, I told you that the tag names live in a different namespace than all the other names in a C program. So in other words, C keeps the structure names in a separate place compared to your function, variable, and type def names. Right? And so these don't overlap. Right? These, as far as C is concerned, these are different things. So you are allowed to write something like that. Right? And so now I can just write qstring instead of struct qstring everywhere. Right? Again, there will be people who tell you this is a bad idea. Right? You're using the same name for two different things. Right? Here we're using a type def qstring, right, which is the same as the tag name belonging to a structure. So for this notebook, instead of writing struct ql stack, I'm going to change the structure name to ql stack underscore tag, right, to emphasize that this is the tag name belonging to the structure. Right, ql stack will be the type def that we provide everybody else to use when they want to use our linked stack. Okay, so in the header file, for our linked stack type, we're going to have our include yard. Right? We're going to have our opaque type. And then we're going to list the functions that our stack will provide. Right? So ql stack init. So that's the function that makes an empty stack, right, and returns a pointer to the newly allocated stack. We've got a convenience function here, is empty, right, returns true if that stack is empty, and returns false if it's not empty. Notice the use of const here, right? So the fact that the s is declared as a const pointer is telling people that this function doesn't change the state of the stack, right? Which is good because all this is doing is returning whether or not the stack is empty. QL stack size returns the number of elements in the stack S. Push pushes that element onto the top of that stack. Right, notice here S is not declared to be a const pointer because we have to change the stack object. Right, when you push something onto the top of the stack, you have to adjust its top pointer to point to a new element. So that cannot be const. Pop removes an element from a stack, so again, that can't be const. Now, the interesting thing about pop is that the function returns a pointer to a stack, right? So it returns a pointer to the popped stack if the function succeeds, but it returns null if the original input S was null as well. And so here the return type is being used for the to indicate possible error condition. Right? It also lets somebody pop a popped stack. Right? So you can pop the stack and then you can pass the result immediately to pop again. Right? Now, when you pop a stack, you probably want the element that was popped. So we need some mechanism to return the element back to the caller. Right? So your choices here, right? If we're going to use the return value to return a pointer to the stack, right? We can't also use it to return the popped value. So here, to get the popped value, the caller provides a pointer to an int object in which the popped element can be written into. Right? So our function is going to write into whatever object that thing points at, right? And it'll store the popped element there. We're going to print a stack. So it's often useful to be able to print out something like a stack or some other collection, right? If only for debugging purposes, right? That might be handy to have. So we're going to provide a function that prints a stack, right? And again, because we provided a function that initializes and allocates a new stack, it would be nice if we provided a function that can deallocate the stack as well. Here we have to provide this function. Right? Because the caller has no knowledge of what's inside the stack. Right? So there's no way for the caller to deallocate the memory used by the stack. Right? They don't know what's in it. They don't know how to navigate the elements in the stack. Right? There's no way for them to deallocate the stack. So only the stack type itself is able to do it. We have to provide a function that can deallocate the memory used by the stack. There's our type def. Our type def was at the top, right? I put it in here. Yes, there's our type def, right? And so that prevents, or that means that people who are using our type, they don't have to write that all the time. They can just write QL stack. I should point out, this doesn't actually introduce a new type in C, right? So QL stack is not itself a new type. It's just a name, right? And that name happens to be mean the same thing as that. So the actual type is struct QL stack tag. Okay, so how do you implement this thing? So if you recall the implementation of a linked stack from Java, from 124, it's more or less the same thing in C, right? Except instead of using new, you're using malloc. And you also have to clean up after yourself. So the destroy function has to clean up our stack. Okay, so what does the implementation look like? So after including your standard library files, you're going to include the header file belonging to your type, right? And so now that declares all of the functions that are in the header file. So it introduces them into the C file itself. Now you have to define the types that you want to use inside the stack. Right, so here's where we declare the definition. Here's where we define the node structure. Right, so this is a stack of int. Right, so we have the element in int, right, and our link to the next node is just a pointer to the next node. Right, we also have to now define the stack structure itself. Right? And so for the stack itself, we're going to keep track of the pointer to the top node, right? And how many elements are in the stack, right? And that's it. Making a new stack. So this is like implementing the constructor in Java. Right? So QL stack new allocates memory for a new stack object. Right? You should know by now that's just using malloc or calloc if you like. So allocate enough memory for a QL stack, right? Set its members to appropriate values, right? So there is no top node in a empty stack, so we set the top node to null. Right? There are no nodes or no elements in an empty stack, so we set its size to 0. Right? And don't forget to return the newly allocated stack. Right? So again, that's almost exactly what you would write in Java, right? In Java, you would not write those 2 lines there, right? But you would write those 2 lines, something that looks like those 2 lines there, right? And of course, in Java, constructors don't return anything, so you wouldn't have that line there. Right? Size and is empty are dead easy, right? So if you want to know, is the stack empty, right? You've got a pointer to a stack, right? So all you do is you look at the size member belonging to the stack, right? If the size is 0, the stack is empty. If it's not 0, it's not empty. The size, well, you just return the size, right? Okay, what about push? So for the push function, what do we have to do? We're making a linked, we're going to represent our stack with a linked sequence of nodes, right? So for push, we have to make a new node to hold the element that was just pushed onto the top of the stack, right? And so we're going to dynamically allocate memory for that node. Right? Why do we have to use dynamic memory allocation in this case? Because the lifetime of the node needs to live as long as the rest of the stack lives for, right? So in other words, the top node can't exist for just the lifetime of the function. So we have to dynamically allocate it. Now remember, if you're going to dynamically allocate the node, right, you have to free it at some point. Right? So keep that in mind, right? Because when we go to destroy the stack, right, it's not just as simple as freeing the top node, right? You have to do some extra work as well. Okay, so to push an element onto the stack, what do? Right? So first of all, we're going to do some error checking. Right? So if somebody passes in a null for the stack, you can't push anything onto a stack that doesn't exist. Right? So here we return null. Right? If S is not null, what do we need to do? We need to make a new node to hold the newly pushed element. Right? So allocate memory for the node. Right? Once you've got the node allocated, you can go ahead and store the element in the node. Right? So NELEM is just equal to the newly pushed element. Right? Okay, so we've got a new top node now, which is going to be N. Right? We need to make N point at the old top node. Right? So you link N to the current top node. Right? So N next just points at S top. Right, the top node of the stack, right? And now you've got a new top node on the stack, so you have to adjust S top. Right? So now S top points at N, right? And because we're keeping track of the stack size, right? Don't forget to increase the stack size by 1 right there. Right? So S arrow size plus plus works just fine, right? That operator has higher precedence than that operator there. Right? And finally, don't forget, we can return the stack S here. All right, any questions there? Okay, what about popping an element off the stack? So when you pop an element off the stack, right, you're going to look at the current top node, right? You're going to grab the element out of the top node, and eventually you want to quote unquote return that element back to the caller. You then need to remove that top node from the stack. And when you remove the top node from the stack, right, that node is no longer needed. So this is one of the points in time where you can now free the memory belonging to that node. Right? So let's see how this works. Okay, so first of all, I'm going to make a pointer to the current top node. Right? I'm going to call it old top. I'm going to remember what is the value currently at the top of the node, right? So I'm going to remember that value. I now need to adjust the current top of the node, right? I want to remove the old top node from the top of the stack, right? So to do that, I can simply adjust S top, right? I want S top to point to the next node in the sequence. Now, in these linked sequences, you have to remember that the way you get to the next node is you have to follow the current top node to get to the next node, right? So the current top node is old top, right? The second node in the sequence is pointed at by old top next, right? And so we can set S top to whatever that points at. Right? You're going to decrease the size of the stack by 1 because we just removed an element from the top of the stack. Right? All right, we're almost done. Right? I have to return the popped element back to the caller, and the way that we're going to return it is we're going to write into the object that's being pointed at by popped. Right? Only this time here, we're going to be a little bit more sophisticated about it. So here, we're going to allow the user to pass in null for popped, right? So if they pass in null for popped, that means they don't care about the popped value, right? And so we're not going to write into their pointer, or write into the object using their pointer, right? If they pass in a non-null pointer, that means they are interested in the pop value, right? So now we should write into that object. Right? So if popped is not null, right, we're going to write into the object pointed at by popped. Right? How do we write into that object? You dereference popped, right? And you store the current element into that object, right? And now you can safely return S, right? So notice here, that's where we're freeing the old node, right? You have to free it because we dynamically allocated the node back in push, right? Now that we're done with it, we have to free it, right? You're going to do it here, right? You can't do it up here, right? Because you can't free the node until you're done using the node, right? I need old top or I need the current top node to get to the next node in the sequence, right? So you can't free the node until you're actually done with it, right? And so that's the appropriate place to do it there, right? I guess you could do it before the return statement as well, right? And that completes the pop method for the stack. And so if you were to compare this to the Java code, right, in Java, you normally would not return a reference to the stack, right? You wouldn't pass in a reference to a stack either, right? The method would be part of the stack class itself, right? So you don't need S, you have this in Java, right? So you'd normally return the popped element over here. Right? And you never care about freeing the node that you just got rid of in Java, right? The Java virtual machine takes care of freeing the memory used by the that's no longer needed by the popped node. Excuse me. All right, so that's pop. That's basically it. So basically, we have print and free left to do. So free is the function that frees a stack. So it frees the memory used by a stack, and you have to remember that that stack might have some elements in it, right? And those elements are stored in nodes that we dynamically allocated, right? And so what does that mean? It means we have to deallocate all the nodes that we allocated that are still in the stack, right? And so that means you have to walk along the sequence of nodes, freeing the nodes as you go, right? And you have to be a little bit careful about how you do this, right? You can't free a node before you get a pointer to the next node, right? Because if you free the node first, there is no pointer to the next node anymore, right? So you have to be a little bit careful about how you do this. Okay, so someone passes in a stack to free, right? If there is no stack, there's nothing to do, so you can just return, right? Now you want to free all the nodes. So to do this, you have to walk along the sequence of nodes, right? And to walk along the sequence of nodes, if you remember from 6.124, typically you just write a little while loop, right? In Java, you would write while the reference is not null, right? And so in C, you're going to do the same thing, right? So starting at the top of the stack, right? As long as there is a pointer, right? As long as there is a top of the stack, right? I want to free that node, right? So I want to free the top node, then I want to free the second node, and so on and so on and so forth, right? Before you free the top node, you need a reference to the next node in the sequence. So the next node in the sequence, the one after n, right, is n next. Right? Once I have that pointer to the next node in the sequence, now I can free n. Right? You can't flip those two around, right? If you free n first, there is no n next. Right? So free the node, right? And now don't forget to advance n to the next node. Right? So n now points at next. Right? So next time through the loop, n is the second node in the sequence. Next will be the third node in the sequence, right? Free the second node, right? Go to the third node in the sequence, right? And so on and so on and so forth. Eventually, n next will be null, right? So when you get to the bottom node in the sequence, n next is null, which makes next null, right? Which makes n null, which stops the loop at the next iteration, right? And so that frees all of the nodes that are currently still in the stack. Right? And once you freed all the nodes, don't forget, you also dynamically allocated the structure that holds the stack. So now you can go ahead and free S. Right? Right? And so there, that illustrates walking along a sequence of nodes. Right? And that's always the same loop. Right? If you ever need to walk along a sequence of nodes, right, starting at some node, right, continue, right, as long as n is not null. Right? At the bottom of the loop, don't forget to advance n to the next node in the sequence. So there's freeing a stack. Finally, printing a stack. So printing a stack is not as easy as you think it might be. To just print out the elements in the stack, it's sufficient to walk along the node. It's sufficient to walk along the nodes in the stack, right? Printing each node as you go. Right? If you want to be a little more sophisticated about it, you can do something like the following. So our print function lets the caller specify a string to print in front of the at the beginning of the string. Right? It lets you print a. It also lets the caller specify something to print after printing the elements of the stack. Right? So pre is the stuff to print before the elements of the stack, and post is the stuff to print after the elements in the stack. Right? S, of course, is the stack whose elements we'd like to print. Right? Okay, so if pre comes in as a non-null pointer, right, we know that there's a string that the caller wants to print in front of the elements, so we'll print that string. Right? Now I'm going to print out top. You might skip this step here, but I'm going to print out top. Right? And now I want to print out the elements in the stack. Right? So I want to walk along the sequence of nodes. Okay, so if the stack is empty, there's actually something to print. Right? Now, the way I'm going to print this is I'm going to print out the element followed by a comma, followed by a space, followed by the next element, followed by a comma, followed by a space. Right? So if the stack is not empty, there's something to print. I'm going to print out the first element. Right? So there's I'm going to starting at the top of the stack. I'm going to print out the first element. Right? I guess what's important to point out here is that I know how to print out the element. Right? It's a stack of int. So I can just use printf%d to print out the element. Right? So that prints the element. And now I want to print out comma space next element, comma space next element, comma space next element, and so on and so on and so forth. Right? So that's why I printed out the first element first. Right? Because the pattern is print the first element, comma space next element, comma space next element, comma space next element, and so on and so on and so forth. Right? Don't forget to move n to the next node in the sequence first, though. Right? And now you loop over the rest of the nodes. Right? As long as there's a node, you can just print the element in the node. Right? So I'm going to print out comma space followed by the element in the node. Right? And then advance n to the next node in the sequence. Right? And so that prints out all of the elements in the node. In the stack. I'm then going to print out the string bottom, followed by whatever else the caller wants me to print out after the stack. Right? And so there's an example of printing out the elements of a sequence. Okay, so here's a little program that demonstrates using the stack. So this basically just shows that it actually works. So this one, what does it do? It takes in an integer value. Is that true? Oh, I know. This one lets you type in the elements of a stack, and then you can print them as you go along. So hang on, just let me get out of here. And we can try this out. I want this one. I think this is QL stack. All right. Okay, so the demo program lets you build a stack of integers. So 5, 7, 2, 6. There we go. Right, and so it starts to pop elements onto the stack. So it pops a 5, a 7, and 2, and a 6. Right. So when you pop push a 5 on top of the stack, right? You can see here that my prefix string is just Q1, right? Then it prints out top, colon, 5, bottom. Right? It also makes a copy of the stack Q2. Sorry, it doesn't make a copy. It makes another stack Q2, and it negates the values here. So you get -5, -7, -2, and -6 on stack Q2. Right? And so when you push all the elements on top of the two stacks, right, there are your two stacks. Right? So 6, 2, 7, 5, right? And -6, -2, 7, -7, and -5. And then it just pops the elements off the stack, off the two stacks. Right? And you can see that the popped values are, in fact, correct. Right? And so it looks like our stack implementation seems to be functional. That shows you, okay, so that shows you how to compile and run the demonstration program there, right? And so there's an example of a type, right, that uses dynamic memory allocation to create a linked sequence of nodes, right? I guess the important things to remember here is that every time you're adding something to the sequence, you're allocating a new node, right? Which means you have to get rid of that node at some point in time, right? And so in the free function, or when you pop an element off the top of the stack, that's where you're going to be freeing the memory used for each node. So you can now take that implementation and implement any other sort of linked sequence, right? So you can do a linked sequence of, you can use a queue, right? You can implement a singly linked list, right? And it's all more or less the same thing, right? You're just manipulating the pointers to the next nodes in all of those different types. So there's one thing that stands out, I guess, compared to Java. Right? And that is, where's our type? Here. So this is in Java, right? So in Java, sorry, where's the C? So our node, right? So our node stores integer values, right? Stores ints. So this is a stack of ints. What if you wanted a stack of something else, right? So suppose you wanted a stack of double, right? What do you have to do, right? And so in C, you need to make another stack class, right? So at least at this point in the course, we would have to make another stack class, right? So instead of QL stack, you might have a QL stack D for a stack of double, right? If you wanted a stack of strings, you'd have to make another stack class, right? And if you wanted a stack of anything else, you have to create another stack class, stack type for each different element type that you want to store, right? You know that in Java, you can make a generic type, right? And so the question is can you make a generic type in C, right? And so the answer is yes, you can, and we'll do that on Monday. But you're going to see that the generic type we end up creating is very different than the one you have in Java, right? It behaves more like something you would create in Python, right? And it also imposes some constraints on how you use it, right? So whoever uses this thing, there are some extra constraints that they have to pay attention to, right? So I'll show you how to implement a generic stack type in the next class. Right? Okay, we're out of time for today, so that wraps things up.